Okay, I'm going to start. Surface characterization is an important part of exploration activities, and LiDAR is a key instrument for this. So we wanted to develop an algorithm to streamline planetary surface characterization for LiDAR products like texture cam and Aegis does for imagery. So constraints on this are that exploration activities require a high level of automation, and we will not have prior knowledge of the terrain at ground level. So based on the concept we developed of general surface divergence, where areas of low interest are non-divergent and areas of high interest are divergent, we decided to use position and normal to characterize planetary surfaces. Using LiDAR as a means that data products will have high dimensionality and high density. So we decided to use a neural network-based machine learning algorithm for this, and we used the adaptive resonance theory for this. So it's a machine learning algorithm that requires no priming or training data. It has the ability to identify new classes in data with no upper limit, and you can classify with the use of a hyperparameter called vigilance, which is denoted by the Greek letter rho, and that is set between the value of 0 and 1. So we cannot develop, we need to generate surface normals mathematically. So we can do this using a standard method of nearest neighbor covariance SVD. So this method plus the adaptive resonance plus some visualization, we can create a pipeline from all these things and we can engage in experimentation with this. So the first set of experiments, we used these dimensional combinations of these dimensions that we call feature spaces, position, normal, and curvature. And then we set the hyperparameter rho to random numbers between 0 and 1. And we've used a data set that was we obtained from the RISE2 project, and that was ground truthed and manually created with expert consultation from them. So this is the data set. This is Kilbourne Hole. So we have 3 areas of significance, ground truth areas. We have a non-divergent area here to the left, and then 2 areas of significance, the incline and the elevated plateau here. So the first set of results are that the network is able to, using manual selection of the rho parameter and manual selection of the feature spaces we use, it's able to classify areas of significance without any training data. So this was a positive result. So we wanted to push this forward. So we decided to do that by testing on more data sets to see how well the network was able to classify more complicated terrain, and also to make the process fully automatic. So that process was a 2-stage process, which we used dimensional reduction dimensional reduction machine learning technique to complete. So that dimensional reduction analysis element came in 2 parts. Selection signal generation and selection signal detection. The generation part consists of the dimensional reduction techniques. So we used LDA and UMAP for this. The signal detection parts consisted of measurement metrics. We use Euclidean distance and F-score, and these detection part is what selects the appropriate classifications from those that have been done. So we also needed a method of evaluating the effectiveness of these selections. So we came up with a 4-point score, with 0 being a random distribution of network classes and 3 being a perfect classification. So this allows us to quantify results in a familiar fashion. So this is our new configuration with dimensional reduction analysis added. And these are our experiments. So we had 50 intervals of rho used. We added 6 data sets, and we had 6 dimensions that we were using, which was about 1,800 experiments. So we added a new data set, which was a simple crater with 1 area of significance highlighted the bowl, and then an area of less significance on the outside. And then we created several synthetic data sets based on that crater that was designed to kind of emulate other terrains in the solar system. And then we created another data set which had geometric shapes in to see how well the network did with this. So the results are that between the detection metrics, the Euclidean distance and the F-score, the F-score was clearly more effective with a higher score here at the bottom. But between the 2, generation techniques, the LDA and UMAP, it's inconclusive because UMAP and LDA, the scores are the same. but the metrics, the scores are higher in both cases for the F score, but between the two things are the same. So we wanted to improve these results to give a definitive optimal configuration. Can we find this? So other workers in this area that were attempting to test machine learning algorithms tried between 10 and 30 combinations of dimensions. So we tried that. We wanted to know if we could improve results by only selecting classifications that had less than 10 classes generated by the neural network. And then we wanted to add very large, high definition point cloud data sets with complex terrain to see how well the network could classify those. So this is our new configuration with our filter added here, and this is the actual curve that we use to filter. These are the new sets of experiments. So we've got 50 classifications again, 50 intervals of row, but now we have 17 point clouds and 15 different combinations of dimensions for about 13,500 experiments. These are the new data sets we added. These were very large data sets. They had to be cut into sub data sets that were so large. And the first one was cut into 4 and this one was cut into 8. So these are the results. So the results show that the out and out winner is the UMAP F score unrestricted with a 76% chance that that network will select a scientifically viable classification. The next highest score was the UMAP F score that was restricted, and that was only 56% chance. So this was very much out in front. And these are some of the classifications here, which we can go through later if people really want to know exactly how to read these. But as you can see, if you look at the distribution of colors, what should be apparent here is that the network has been able to find structure. So the columns on the right and in the middle are the ground truths that are isolated from the main. And you can see that when we compare them to the column on the left, that actually the distribution of colors clearly shows that it's found the structure in these terrains. So in conclusion, we demonstrated the viability of adaptive resonance neural network as a generalized geological feature classifier that requires no training to identify formations on planetary surfaces. We applied this in a self-contained end-to-end pipeline designed to extract geologic features from high-density point clouds based on operator input. We then demonstrated the same process as a fully automatic process without any operator input by incorporating dimensional reduction to detect the classifications automatically. And we investigated the effect of increased numbers of different dimensions on the classifications. And we applied this to a number of natural and synthetic data sets from various sources with very positive results. So what we're hoping is that a system with these attributes can be incorporated into workflows for human and robotic planetary exploration in the future. So I know that was a bit fast. I hope I haven't gone too far over time. So if anybody has any questions, I'm open to answering.